Now in this question, we have a boo starting at an initial height, and he will swing down to a lower position, maybe about right here. So essentially, a boo is a pendulum. Now, because we're not resting on a surface, there is not a normal force to be calculated in this case. But assuming he starts from rest, our goal then is to find his velocity at the lowest position right here. Now, it does make sense to place the origin at that lowest position. So there's our origin. That's where gravitational potential energy will equal to 0. Now, again, since we don't know the exact height of a boo or this location here, the origin location at the lowest position is the best choice. Now, our first question we should find again is the height of a boo at this angle, and we use the length of the pendulum minus the length of the pendulum times the cosine of the angle theta. I look and I say, well, 3.5 is my length here, so I go 3.5 minus 3.5 cosine of 54. And then my height is equal to 1.44 meters. Okay, now it's time to go to our conservation of energy equation. And one more time ask ourselves all of the same questions. Is a boo moving initially? Well, no, he is at rest, so there's no kinetic energy. Is he above the origin? Well, yes, he has swung above the origin here initially, and he's not moving. So we'll give him some gravitational potential energy. I'll start with 3 boxes. I look and say, are there any springs attached anywhere? No, I don't see any springs, so there's no elastic potential energy. And one more time, I want to determine if work is done. Well, if work is done, there would be an applied force acting on a boo, trying to make him go a certain direction or anything through a distance, and I don't see any applied forces there. So the beginning energy for him is all gravitational potential energy. He's now going to swing down to the lowest position here, and I'll ask the question for the final case, which will be right here. So beginning case, this location. Final case is right here. Is he moving there? Well, it's very logical for him to be moving at that instant, unless he hits some kind of a wall, and we wouldn't do that to a boo. So we'll give him some kinetic energy. He has returned to what we defined as the origin. So for this question, there is no gravitational potential energy, so I leave that blank. And I go, are there any springs attached suddenly? No, I don't see any springs attached at all, so no elastic potential energy. Now we go to thermal. There would be a small amount of air resistance acting on a boo as he comes down. I don't see a description of air resistance anywhere, so I'm going to assume in this question that this is negligible, so I will not call any thermal energy possible here in this case, or I guess we just say we ignore it. I don't see him sliding on the surface to give me any indication there would be thermal energy either. So I would say that it's all kinetic energy in the final case. Okay. Well, again, that's reasonable for our approximation because it would be a small amount of air resistance. So then gravitational potential energy is being converted into kinetic energy. And I look and I say, well, I don't see a mass for a boo, so I will give him just the letter M to represent his mass. Okay, let's fill in and solve for velocity. So gravitational potential energy is then going to be M times 9.8 times the height that I previously solved for, 1.44 meters, equals 1/2 M, and I look and I go, well, I don't know velocity, and one more time, my kinetic energy equation will have a velocity v in it, and that becomes my variable. Okay, of course, it would be velocity squared. And I note that masses, one more time, can cross off. I don't need to know that, and then I just solve for velocity. And his final velocity is 5.3 meters per second. And that's how you find the velocity at the bottom of the pendulum.